Hello everyone and welcome. Today we are diving into a totally crucial part of our university software engineering program. We're going to explore database performance tuning and query optimization. I have to say I'm absolutely thrilled to guide you through this, because knowing how to make a database run efficiently, well, it's basically a superpower in the software engineering world. If you've ever sat there staring at a screen just waiting ages for a page to load, you know exactly why this matters. So grab your notebooks, get comfortable, and let's unravel the actual mechanics behind high-speed data retrieval.
Okay, let's jump right in with the ultimate golden rule of our entire discipline. It goes like this. Good database performance starts with good database design. No amount of fine-tuning will make a poorly designed database perform as well as a well-designed database. This is the core philosophy that anchors everything we'll talk about today. Before we even think about tweaking settings or observing optimization behavior, we absolutely must acknowledge that structural design is paramount. Seriously, if your tables and relationships are a mess, there is no magic trick in the world that's going to save your system's performance.
To keep us on track, here's our program for today. First, the golden rule. Second, how queries are processed. Third, the magic of indexes. Fourth, the query optimizer. Fifth, SQL performance tuning rules. And finally, a quick summary and next steps.
Let's start with Section 1, the golden rule. So, assuming we have a solid foundational design, which, again, is completely non-negotiable, we generally divide performance tuning into two distinct camps. We've got client-side tuning and server-side tuning. On the client side, well, that's on us as software engineers. Our job is to formulate really precise, highly efficient SQL queries that ask the database for exactly what we need without wasting any resources. On the flip side, server-side tuning is all about the physical environment and the database management system itself. It involves configuring the DBMS software, allocating more RAM to memory caches, or upgrading to faster hard drives. Essentially, it's the hardware and architectural muscle that actually supports our client-side code.
Moving right along to Section 2, how queries are processed. Imagine the exact moment a user clicks a button and hits execute on a query. What actually happens on the server end? It's not just a single action, it's a multi-step journey. The DBMS processes every single query in three chronological phases: parsing, execution, and fetching. We're going to break down each of these steps right now so you can fully understand the system's mechanical behavior.
Let's kick things off with the parsing phase, which is incredibly crucial. When the DBMS receives your SQL code, it doesn't just run it blindly. First, it checks the syntax to ensure it's written correctly. Then it checks the data dictionary to validate your access rights. Are you even allowed to see this data? After that, it decomposes and analyzes the query to generate what we call an access plan. Definitely highlight this, as it's a highly testable definition. An access plan is the mathematical roadmap containing the exact series of steps the DBMS will use to retrieve your data as efficiently as possible. And here's the clever bit: once created, the database actually caches this roadmap. So if someone runs the exact same query again, the system can completely skip the parsing phase and save some seriously valuable time.
Once that access plan is ready, the execution phase begins. This is where the real heavy lifting happens. The DBMS runs the access plan, acquires any necessary locks to protect data integrity, and physically retrieves the data blocks from the slow hard drive, pulling them right up into the fast RAM data cache. Now, during execution, the DBMS might use different table access methods. It could do a full table scan, or it might use a much faster index scan, and the method it chooses drastically impacts how fast this phase actually completes. Finally, we hit the fetching phase. This is where the DBMS takes all that retrieved data, sorts it if necessary, and coordinates sending the final result set back across the network to the end user.
Which brings us to Section 3, the magic of indexes. So the big question is, how do we speed up that heavy lifting execution phase? Well, we use the single most important tool in our arsenal, but first, we need to state a universal truth of computing. The primary goal of query optimization is to minimize incredibly slow disk I/O. That means minimizing input-output operations to the physical hard drive. Reading data from RAM is lightning fast, but reading from a physical hard drive? It's like waiting for dial-up internet in the 90s. Without an index, a database often has to perform a full table scan, meaning it reads every single row just to find one specific record. It's literally like reading a 1,000-page textbook cover to cover just to find the definition of one single word. An index acts exactly like the index at the back of that textbook. It lets the system jump straight to the exact row in RAM, bypassing all that unnecessary reading.
Now you might be thinking, great, let's just index every single column. But we can't do that. Doing so would completely overwhelm the system whenever we tried to insert or update new data. So how do we choose what to index? We rely on a vital metric called data sparsity. Data sparsity refers to the number of different values a column can actually have. A column with high sparsity has many unique values. Think of a date of birth or an email address column. Almost everyone's is different. On the other hand, a column with low sparsity has very few unique values. Think of a biological sex column, which might just be M or F. Knowing the sparsity metric is exactly how we decide which type of index will actually be effective.
And that concept of data sparsity leads us directly into our two main types of indexes. First up is the B-tree index. Picture an upside-down tree structure. This is absolutely perfect for high sparsity columns, like customer last names. The database navigates down the branches of this tree to find specific, highly unique records incredibly quickly. But then, contrast that with a bitmap index. A bitmap index uses a simple bit array of zeros and ones. This is ideal for low sparsity columns. For example, if we have a region code column with only 4 options, say northwest, southwest, northeast, and southeast, the bitmap index just flips bits on or off. It takes up very little space and is blindingly fast for filtering massive datasets by just a few repeating categories.
Let's move on to Section 4, the query optimization.
Indexes are basically magic, but the database still needs a brain to actually decide when and how to use them. Just because an index exists doesn't automatically mean it's the fastest route for every specific query. For this brain to make good decisions, it needs up-to-date information, which we call database statistics. These are measurements gathered by the DBMS about its own objects. We're talking about things like the total number of rows in a table, the number of disk blocks being used, and the index sparsity we just talked about. If these statistics are outdated, the optimizer is essentially flying blind, and it will very likely choose a terribly inefficient access plan.
It's really interesting how this has evolved. Historically, databases used what's called a rule-based optimizer. This was an older approach that used preset, hard-coded rules to determine the best execution path, completely regardless of what the actual data looked like. Thankfully, today, modern systems use a cost-based optimizer. This is a highly intelligent mode that uses those database statistics we just mentioned to mathematically calculate the actual cost in terms of disk I/O for several different potential plans. Then, it automatically selects the cheapest, fastest option for us.
Section 5, SQL Performance Tuning Rules.
So now that we understand how the server optimizes our requests in the background, how can we as software engineers write our client-side code to help the server run even faster? Let's go over some really practical guidelines for index creation. First, you should absolutely create indexes for attributes that are heavily used in your where, having, or order by clauses. These are the columns the database is actively searching or sorting all the time. Second, target columns with high index selectivity, meaning the index will actually narrow down the result set significantly. Third, do not use indexes in very small tables. If a table only has, say, 20 rows, it's actually faster for the DBMS to just scan the whole table than to bother reading the index first. And finally, as a general rule, avoid indexing tables with low sparsity. The database will just end up reading most of the table rows anyway, making the index extra, totally unnecessary work.
Okay, so the really crucial point here is how we actually type out our queries. Here's some everyday syntax rules you really must memorize. Number 1, equality comparisons, like equals, are processed much faster than inequalities, like greater than or less than. Number 2, comparing numeric data types is mathematically faster for the CPU than comparing string or character data. Number 3, try to avoid the not operator and the like operator whenever possible. Why? Because they usually force the database to abandon our beautiful indexes and perform a full table scan instead. And number 4, this is a brilliant developer trick. In a where clause with multiple and conditions, always put the condition that is most likely to be false first. Since it's an and statement, if the very first condition is false, the DBMS just stops checking the rest immediately, which saves tons of valuable CPU cycles.
And finally, Section 6, Summary and Next Steps.
You made it. Congratulations on navigating what is honestly an incredibly dense and technical topic. Let's do a quick wrap-up review, starting with some core definitions you'll definitely need to know. Remember, the access plan is your mathematical roadmap generated during the parsing phase. Data sparsity measures the number of unique values in a column. For high sparsity data, we lean on the upside-down B-tree index. And for low sparsity data with repeating categories, we deploy the bit array bitmap index.
Beyond just definitions, you really need to understand the overarching mechanics we discussed today. Never forget that good design always precedes optimization. The entire goal of all our tuning efforts is minimizing slow disk I/O. Every single query processes in 3 distinct phases: parsing, execution, and fetching. And finally, modern cost-based optimizers are completely dependent on keeping database statistics up to date. Rote memorization just isn't enough here. You have to intuitively understand how all these mechanical parts interact with one another.
Before we wrap up, I want to leave you with a provocative question to ponder before our next meeting. If we can perfectly tune a single server to run queries at absolute lightning speed using these rules, how does all of this change when our database isn't just in one room, but is actually scattered across multiple servers around the entire world? Think about the network delays and the immense complexity of coordinating all that data. That is exactly the challenge we will tackle in our next explainer on distributed database management systems. Thank you so much for your focus today, and I'll see you next time.